Hello viewers, in this video I will discuss about textures of igneous rocks part 2. In this discussion, the outline of the discussion is mutual relationship amongst crystals and non-crystalline matrix. I am directly coming to mutual relationship, but before that I will discuss what I have discussed in part 1. In part 1, I have discussed about crystallinity, granularity, shape of the crystals. Now, the fourth one is mutual relationship among crystals and non-crystalline matrix. This will be discussed in this video. So, equigranular texture, microgranitic texture, orthophoric texture and felsitic texture. Equigranular texture is of three types basically: microgranitic, orthophoric and felsitic. Then inequigranular texture is of three types: porphyritic texture, picolitic texture and intersalter texture. And third one, the last one, is miscellaneous textures, and lastly we will summarize the entire discussion. Let us recapitalize that what we learned in the previous lesson. We have discussed three textural elements: crystallinity or degree of crystallization, granularity or grain size, and shape of the mineral grains. Now in this lesson we will discuss in detail about four textural elements, which is called mutual relationship among crystals and non-crystalline matrix or glass. So let us start with mutual relationship between crystals versus non-crystalline material. The first category is equigranular texture. Equigranular texture is a type of texture where grains are almost equal in size in all the three dimensions. The best example is granite and gabbro. There are three subtypes such as microgranitic or fine-grained rock with anhedral or subhedral grains, orthophoric texture, which is called fine-grained rock, euhedral grains, and third one is felsitic or microcrystalline or very fine-grained texture. Now under this category, the second one is inequigranular texture. The grains are of unequal size. This is contrasting to the first one category. In first category, you have all the grains of almost equal size. But here, there is a difference in the grain size. All the grains are of unequal size. There are three subtypes such as porphyritic texture, picolitic texture and intersalter texture. Seriate texture is also discussed in this category, is marked by gradual grain size difference. Now let us first discuss about the porphyritic texture. Porphyritic texture, in this case the phenocryst or the larger size crystals are embedded in a fine-grained ground mass of smaller grains or microcrystals or sometimes glass. It is visible megascopically and microscopically both. They are formed due to change in physicochemical conditions, molecular concentration and insolubility. The microphenocryst and finer phenocryst and megaphenocryst is a coarser phenocryst grain. These are the two important terms which are commonly used to describe porphyritic texture. One is microphenocryst. The finer grain size crystals are called finer phenocryst or microphenocryst, whereas the large size crystals embedded within the fine grain matrix is called megaphenocryst, which is coarser in grain size. Let me show you a hand specimen of porphyritic texture which shows phenocryst in mottled pink ground mass and B micrograph of a basalt that shows plagioclase phenocryst in a ground mass which consists of fine-grained plagioclase agate, glass and iron oxide. In my right hand side you can see. The porphyritic texture is of three important types, and they are categorized as vitrophyric. Vitrophyric means when large size phenocryst is embedded within a glassy ground mass. The texture is called vitrophyric. The felsophoric, in case of felsophoric texture, the phenocryst enclosed by cryptocrystalline ground mass. Here the ground mass, grain size of the ground mass is slightly larger in case of felsophoric texture. Whereas glomeruloporphyritic texture is a term used to describe early formed olivine, pyroxene and plagioclase phenocryst. They are clubbed together forming distinct clusters or crystal aggregates. These aggregates are lying within the fine-grained crystals of clinopyroxene, plagioclase or sometimes magnetite or some altered minerals. Let me show you the three important types of porphyritic textures. First one on my left hand side is vitrophyric texture. In this case, the plagioclase phenocryst in glassy ground is lying within the glassy ground mass. All around the grey colored, white grey colored plagioclase crystal, you have a black glassy ground mass. Whereas in felsophoric texture, the greyish black plagioclase phenocryst is lying within the cryptocrystalline ground mass. Third one category, the glomeruloporphyritic texture. In this case, the cluster of plagioclase phenocryst crystals, they are lying within the ground mass consisting of fine-grained plagioclase, agite, pelagonite. Pelagonite is an altered product of mafic minerals and iron oxides. The second one important category, which is called picolytic texture. In this case, the larger grain encloses smaller mineral grains. The larger crystal is called occicrust, whereas the enclosed grains are called cadocrust. The picolytic texture is of three different types. First category is ophitic texture, occur in fine to medium grained mafic rocks, for example dolerite, basalt, where large agite crystals they enclose smaller plagioclase laths. Number two, subophitic texture, agite grains are smaller and partially enclose plagioclase laths. The plagioclase laths are partially inside the clinopyroxene grains and partially outside it. Ophitic and subophitic textures result from nearly simultaneous crystallization of plagioclase and pyroxene minerals that differ in their crystal properties. Third one is hyalophytic, is similar to ophitic texture, but diversely oriented plagioclase grains are commonly surrounded by glass. I will show you all the three types of texture in the following slides. And third one is intercertal or intergranular texture. In case of intercertal or intergranular texture, volcanic glass is replaced by secondary alteration product like pelagonite. When randomly oriented plagioclase laths touch each other to form a network and polygonal interstitial spaces are filled up by granular anhedral pyroxene grains, the texture is known as intergranular texture. When interlath polygonal spaces are filled up by glass or its devitrified product, the texture is known as intercertal texture. I will show you all the types of texture in my slides here. The first one, photomicrograph, show ophitic texture. On my left hand side, a big clinopyroxene agite plate encloses small laths of plagioclase, and B, subophitic texture, where the plagioclase laths are partly inside the clinopyroxene grains and partly outside of the clinopyroxene grains. This photomicrograph shows intergranular and intersurtal textures where polygonal spaces between plagioclase laths are filled up by secondary altered products of glass such as pelagonite, pela means pelagonite, and also agate or clinopyroxene. The intergranular or interlocking texture is randomly oriented microlithic plagioclase and abundant pyroxene FeTi oxide and olivine grains form light interlocking texture. You can see in this photomicrograph, you have randomly oriented microlithic plagioclase. Grey colored rod-like microlithic plagioclase is lying on my left hand side slide, and abundant pyroxene and iron oxide and olivine grains are found within the interspaces of these rod-like microlithic plagioclase grains. See here, on my right hand side, the next slide, the photomicrograph showing network of randomly oriented microcrystals of plagioclase and pyroxenes. Now, the fourth category we will discuss about is the intergrowth texture or intergrown texture. In case of intergrown texture, the interlocking of two diverse mineral grains formed by simultaneous crystallization of two mineral components of the magma at a particular temperature called eutectic crystallization. Such texture is called graphic texture. The rock is called micrographic rock, and the rock is also called as granophyre. The intergrown texture is very common and it has been formed by the process of eutectic crystallization. Let me discuss in details about the eutectic crystallization, where two components, AA component and BB component. AA component has a high melting point. It starts cooling from BB point and it follows a liquidus curve. Similarly, the AA component starts having slightly lower melting point, start crystallizing from MP point, and it follows a curve which has a degree of freedom of 1. Now these two curves, they meet together at one point which is called eutectic point, where the degree of freedom is 0. Below this point, you get mixed crystals formed having composition of AA plus BB. Now graphic texture is shown here, which is formed by eutectic crystallization of two mineral components. It is a common texture found in granite formed by intergrowth of quartz and orthoclase, where quartz blades align parallel to well-defined crystallographic orientation of K feldspar. K feldspar is a host, whereas the other mineral is quartz is present in the form of a blebs. On my left hand side, A has an elongated grey quartz blebs. In white orthoclase, host forms graphic texture. In hand specimen, it can be seen quartz as a bleb and thin section of an interlocked quartz blebs in orthoclase matrix, and C is the same, almost it is a sketch of a graphic texture where the two quartz grains are there, and in between these two quartz grains you get formation of or interlocking of the orthoclase crystals. Now I am citing an example of potash granite. In this case, orthoclase showing perthetic intergrowth. Perthetic intergrowth is, you can see the vermicular quartz blebs are there, they have been grown and forming a perthetic intergrowth. An intergrowth of vermicular quartz in a sodic plagioclase host, commonly in contact with K-rich alkali feldspar. The texture is called myrmekitic texture. What is the origin of this myrmekitic texture? It is originated by direct crystallization or replacement, or originated in subsolidus unmixing of K-bearing plagioclase in a ternary feldspar system. The myrmetic texture is also known as symplectic texture also. It is formed by intergrowth of worm-like quartz rods in the plagioclase, which is called oligoclase also, and the example is granite. Here I am showing the perthetic texture, where the exsolution of alkali feldspar and albite produces perthites, which comprises thin strings, films and patches of albite oriented within K feldspar host, for example orthoclase or microcline. The microperthetic texture is the texture which is resolvable under the microscope. It is commonly developed in coarse plutonic rocks like granite and gabbro. Then I have discussed about the perthite and microperthitic textures. But there is another variety called antiperthetic texture. In this case, it is the reverse of the perthetic texture. In this case, the blebs and patches of orthoclase or microcline occur with plagioclase and give rise to antiperthitic intergrowth. I would like to show you this texture with the help of a thin section. Here, the complete solid solution and orthoclase albite eutectic system with solvus involves separation of two solid phases from a homogeneous solid solution caused by difference in size of K ions. K means potassium ions having an ionic radius of 1.59 angstrom and sodium ions having a radius of 1.24 angstroms. So these two ions, they are mutually replaced and giving rise to a formation of the texture. When bulk composition in K-rich lamellae of Na-rich feldspar form in K-rich host, you get formation of perthite. When bulk composition is Na-rich and lamellae of K-rich feldspar form in a Na-rich host, the texture is called antiperthite, and I tried to show you with the help of two subsolvers in my diagram here. Now perthetic texture, it can be seen under the microscope, and where you find the perthetic texture, you have a small lamellae. They have been grown inside a host of K feldspar. Now we will discuss about another texture or structure called as corona texture. Corona resulted from reactions in magmas and form concentric arrangement of minerals. Zone of reaction produces surrounding a mineral called a reaction rim or caliphatic borders. Zone of reaction products surrounding a mineral is called reaction rim or caliphatic border. For example, olivine is surrounded by pyroxene rim. Successive rings may be around central mineral. Now reaction rims, they are the product of discontinuous reaction relations. They indicate discontinuous reaction relations in fractionating magmas and are recorded in a reaction rim that surrounds an anhedral partly reabsorbed grain of another mineral. Magmatic texture in which more stable mineral surrounds an earlier formed less stable mineral that was not completely reabsorbed in a reaction relation. The rim and rimmed mineral constitute a reaction pair. Mineral which formed at the expense of the other mineral is in a reaction relations with stably coexisting mineral melt. So these reaction rims or the pair of minerals is also called as reaction rims. Now another growth which is discussed in this category is X solution intergrowth. X solution intergrowth is a product of the process of releasing excess volatiles from an oversaturated melt. For example, pyroxenes, magnetite ulvospinel, solid solutions, and alkali feldspar when crystallized in slowly cooled magma as homogeneous minerals from the melt, exsolved at subsolidus temperature into a stable coexisting crystalline phase. The exsolution texture is perthite, an intergrowth of sodium and potassium rich alkali feldspar by unmixing below alkali feldspar subsolvus temperature. In this slide, I have tried to show you the image of scanning electron micrograph showing cubic A, see the photograph A, where cubic, B triangular, and C prismatic, and D enclosed chain-like and anhedral grains and reniform masses of magnetite, ulvospinel, ilmenite, and hematite minerals. Ilmenite 1001 lamellae exsolved from the remaining cube-shaped magnetite. Irregular projections of magnetite and ilmenite are due to unmixing. Ilmenite lamellae vary in size and lie parallel to 111 plane of the magnetite. Figure-shaped residual areas are formed by replacement of ilmenite. Now, miscellaneous texture. These textures cannot be categorized under any of the four previously discussed categories. Miscellaneous textures. Under this category, we have directive texture, trachytic texture, eutectitic texture, texture due to devitrification, spherulitic texture, and spinifex texture. The directive texture, magma during crystallization, mineral grains are directionally arranged from form flows, structures, or bends. The direction of flow may be interrupted by early formed crystals, but flow bands form a line without distorting the bigger crystals. Such texture is known as flow texture. Flow texture in rhyolite, where plagioclase crystals arranged parallel to magma flow. Now, trachytic texture in volcanic rocks such as trachyte and basalts. In basalts, calcic, plagioclase, glassy, cryptocrystalline materials show parallel alignment and preferred orientation due to flowage of magma in a molten state, referred as trachytic texture. I have shown these two textures under the photomicrograph and a sketch also. The eutectic texture is where the parallel pumice fragments in welded imbrigites formed by consolidation of pyroclast and ash flows. Wavy lamination spin around volcanic lithic fragments show flow pattern as dark bands. Stretched lithic pumice and fragments aligned and welded together with devitrified cryptocrystalline ground mass. See the black bands in the rhyolitic specimen here and embedded within the orthoclase ground mass. And on fine-grained glassy pyroclastic rock showing eutectic texture, notice welding of stretched pumice fragments. Devitrification. Glass is a metastable material. Over a long time, it develops irregularly ordered atoms and molecules and forms cryptocrystalline matrix. The process is called devitrification. Devitrification, thus glass yields cryptocrystalline matrix and yields felsitic texture, and rock is known as felsite. Pearlitic cracks in crystals are evidences of their original glassy condition. They are orbicular cracks in devitrified rocks formed by contraction of rapid cooling of magma. Here the cracks are shown here in gray color in the photomicrograph. The devitrification is also shown here in a devitrification of trident shaped glass shards in ignimbrite. Spherulitic texture. Rapid cooling and crystallization of viscous magma yields spherulitic texture. An aggregate spherulitic texture is an radiating arrays of needle common in glassy fabric rocks shown here in the slide. Spinifex texture is an randomly oriented fine-grained crystals or acicular olivine crystals formed by rapid cooling of ultramafic lavas commonly found in comatiites. and comatiite is an ultra-basic rock of volcanic origin. Listeners, here I would like to summarize the entire discussion here. We discussed about various textures resulting due to mutual relationship between crystals versus non-crystalline material, such as types of equigranular and inequigranular textures. The types of inequigranular textures are porphyritic, picolitic, intergrown texture, corona, reaction rims, trachytic texture, devitrification. With this, I will end up my talk. Thank you very much.